absolute value functions, there's not a whole lot new in this section for you. But first of all, I want to talk about the function f of x equals the absolute value of x. This actually can be described as a piecewise function. So if you think about it, if x is greater than or equal to 0, then we just get the line y equals x. So we would have this portion here, the identity line. So I'll draw that in. And then for the other side, if we have the opposite of x, when x is less than 0, then we're going to get this portion here. Notice the line is going, it has a negative slope. So here's my graph. Now, we could have chosen to put the equal to part down here and it really wouldn't have mattered, but typically an absolute value function is defined this way as a piecewise function. Again, we've got this line over here is the identity line, y equals x, and over here we have y equals negative x, or the opposite of x, for these values in the domain. If we are going to graph the function f of x equals 2 times the absolute value of x minus 1 minus 3. Very familiar to you. You know this is going to go to the right 1, down 3, and we're going to vertically stretch by 2. And we can go with our old method, how we always did, because we actually have the function here. So we can use our locator point and do what we did before. So I'm going to move it to the right 1 and down 3. I guess I should label these. And then from there, it's vertically stretched. So instead of the identity line being up 1 over 1, we're going to go up 2. It's like, because we're stretching it by 2. And the same thing right here. And then we get our graph. Okay, let's go ahead and do the domain and range. So for our domain, we're going to have all real numbers. So I'm going to say negative infinity to infinity. And our range, notice that the lowest value is negative 3. So we're going to say negative 3 to infinity. Example 2. Now on this one, you're being asked to write an equation for the function that was graphed. So the first thing I'm going to do is find my locator point. And if I do that, I went to the right 3 and up 5. So my vertex has moved to 3, 5. Notice that it opens down. So that means it's been reflected across the line, across the x-axis. So that was a vertical reflection, but we also know what that means, that we're going to have a negative sign in front. And then we can use, notice that it is actually vertically compressed because it's wider. So you can kind of see what, we know it's negative. I'll leave a little space there. We know this is going to be x. We went to the right 3, so that's going to be minus 3. And we know we went up 5. So then the question is, what goes here? Well, if it had been just a 1, then we would have gone down 1 over 1. But notice we went down 1 over 2. So it's like having a slope of a half, our rate of change. So that's actually the value that goes here. So we would get this for our equation. Now, you actually can do this equation, and let me just show you this other option. We could also have thought of this this way. Left the negative out front and brought the 1/2 inside. Because it's as long as we leave the negative outside, because it's a positive a half, this actually is equivalent. You can check it out for yourself. Type this into y1 in your calculator and this into y2, and you'll see that it actually traces over the same graph, so it is the same. This, we're looking at it as a vertical compression. And if you do it writing it the other way, then we're thinking of this as a horizontal stretch. And they are equivalent, but it's fine to stick with your old way. So we're also going to review in this section solving absolute value equations. I just want to remind you, if you took the absolute value of 5 minus 2, you get 3. If you take the absolute value of 2 minus 5, you also get 3. So what that tells us is the order of subtracting, which normally matters, yields the same result if you're talking about the absolute value. So using that same idea here, where I could switch the order and it didn't matter, if I had the absolute value of 2x minus 3 equals 5, I could say that 2x minus 3 is 5, or I could switch the order and say 3 minus 2x is 5, and I can get my two solutions. Now, we didn't do it that way because sometimes it's not subtraction, sometimes it's addition. So, sometimes there's other operations involved. So it actually, we have a system that will kind of always work and make sense for us. So I want to show you with the method that we did in Algebra 2. We started with our absolute value equation and we broke it into two cases. And we said, okay, maybe the difference between those two values is 5, or maybe the difference between those two values is -5 was our second case. And we solved it that way. So I would add 3 and I get 2x equals 8 and divide by 2, so I get x equals 4. Over here, I'm going to add 3, I get -2, and here we get -1. So notice that you get the same values. I still got 4 and -1. But again, we can stick with the way that we did it before. I just wanted to point that out to you. So what if we graphed the related function? So what would that look like? So if I said f of x equals, and I'm going to subtract the 5, so I would have the absolute value of 2x minus 3 equals 5. And if we actually graphed that, and let's do that on our calculator. What do you know? I already have it there. So I'm going to go ahead and graph this, and you'll see this function. And you can actually do second calc 0. We're going to find the zeros of the function. A left bound, you can use the arrows to do the left bound. And then I'll use the arrows to do the right bound, and in between to make my guess. What do you know? It's -1. And if I do second calc 0 again to find the other solution, this time instead of the arrows, I think it looks like it's 4. Actually, we already know that. So for a left bound, I'm going to put in 2. For a right bound, I'm going to put in 6. And for a guess, I'm going to put in 4. And then it tells me that. So you don't have to use the arrows. You can actually just type in a number that's on each side. So there's another way that we can confirm that. Now remember, with absolute value equations, sometimes we got no solution. Sometimes we got one solution because another one didn't work. And sometimes we got two solutions. Well, if you think about the graphs, that's because looking at a graph here with absolute value, sometimes if you graph the related function, sometimes it doesn't cross the x-axis. Sometimes it's sitting, or it could be hanging upside down from the x-axis, and sometimes it crosses twice. So we get 0, 1, or 2 solutions when we are solving absolute value equations. One last example, the tolerance for a ball bearing is 0.01. So that's the allowance from what it's supposed to be. It could be 0.01 greater in the measurement or 0.01 less than, but that's the tolerance. That's all that's allowed. If the true diameter of the bearing is to be 2.0 inches and the measured value of the diameter is x inches, express the tolerance using absolute value notation. So this is what it's supposed to be, and this is what it's measured. And the difference between those values has to be less than or equal to 0.01. It's okay if it's less than that, but it can't be greater than that. So we could write that, it's the difference between, so I'm going to write that as x minus 2.0. is less than or equal to 0.01, but we don't know if it's x minus 2 or if it's 2 minus x, because we're allowed to go either way. It could be 2.01 or it could be 1.99, and that would be allowable. So what we do is just do the absolute value of that, which means it would be equivalent if somebody wrote this instead. That would be fine. Usually you'll see it written this way with the variable first, but this would be equivalent. Since it's in the absolute value, we could switch those around. So this actually would be your absolute value expression that would satisfy that question.